In this video, I'm going to do a couple of practice problems related to Heisenberg's uncertainty principle. So we're going to think about a ping pong ball, and it's moving at 11 meters per second. So the average person would hit the ping pong ball with enough force to make it move 11 meters per second. And we're going to assume that we know the position of that ball within 680 nanometers, which is a wavelength of red light. So if we can see it, then it doesn't look blurry or anything, like we're actually seeing the ball itself. So we know within a wavelength of red light. And so we want to know what the uncertainty in the speed is of the ping pong ball. So the equation that we're going to use is delta x times m delta v is greater than or equal to Planck's constant divided by 4 pi. So what this is actually saying is the uncertainty in the position, that's what our delta x is, multiplied by the uncertainty in the velocity or speed is greater than or equal to Planck's constant divided by 4 pi, which has to do with the size of the particle. Now, the reason why we've written this as m delta v is because there's no uncertainty in mass. So we're just looking at uncertainty in position and uncertainty in speed. Now, you don't have to be worried about this greater than or equal to sign. You can treat it just like an equal sign when you're doing the math. So let's take a look at this. So let's take a look at what information we have. We know that the uncertainty in our position is 680 nanometers, which is 6.8 times 10 to the minus 7th meters. The mass of a ping pong ball is about 2.7 grams, and we have to convert that to kilograms to give us 0.0027 kilograms. Planck's constant is 6.626 times 10 to the minus 34th joule seconds. And 1 joule is a kilogram meter squared per second squared. So now the only thing that we don't know is our uncertainty in our speed. So I'm actually going to start by rearranging this equation to solve for the variable I care about, which is the uncertainty in the speed. And again, you don't need to be worried about that greater than or equal sign. You can treat it just like an equal sign. And so that would mean that we would have the uncertainty in our speed greater than or equal to h divided by 4 pi times our mass times the uncertainty in our position. So now we can go ahead and add in our values. So we have delta v greater than or equal to 6.626 times 10 to the minus 34th kilogram meter squared per second squared times seconds. That's our joule seconds. Divided by 4 pi times 0.0027 kilograms times 6.8 times 10 to the minus 7th in meters. So let's check our units. So we get rid of one of those seconds. We get rid of one of those meters and the kilograms. And we're left with units of meters per second, which is good because we're asking for uncertainty in the speed. So if we work this out, we get a value of 2.88 times 10 to the minus 26th. So that is incredibly small compared to what we have observed for the ping pong ball. Now let's take a look at something much smaller than a ping pong ball and calculate the uncertainty in the position of an electron. So we're going to start off with our same equation here, and we know the velocity to within 1% of 5 times 10 to the 6th meters per second. So here we're going to start off by figuring out what the uncertainty is in the velocity. So we will have to actually do a little bit of calculations to get this value here. And so we do that by 5 times 10 to the 6th meters per second, and we multiply that by 0.01, which is 1%. And that gives us the actual uncertainty of 5 times 10 to the 4th meters per second. And so that's our uncertainty in velocity. And then we know the mass of our electron, and that is 9.109 times 10 to the minus 31 kilograms. So now what we're going to do is solve this equation here for delta x. So our delta x is going to be h divided by 4 pi times m delta v. And we can go ahead and fill this in with our values, remembering always to do our units. And we'll cancel them in the same way that we did before. And we'll see that our uncertainty is 1.16 times 10 to the minus 9th meters. So what does that really mean? Well, if we look at how big an atom is roughly an angstrom. So if you have 1 angstrom, that's 1 times 10 to the minus 10th meters. And so if you compare these two, what you see is that this is 10 times the size of the atom. So this is why the uncertainty for the position of an electron has an effect on what we know about that electron. Compared to something like a ping pong ball, there's no way that you're going to be that off in the location or speed of a ping pong ball because the ball is so much greater than the uncertainty. And so this is why the uncertainty principle actually matters for something that is small versus something that is big, because the circumference or diameter really, really does matter there. All right, so tips and tricks for these types of problems: do not be afraid of this sign here. Treat it like an equal sign. And don't forget to keep track of your units.